Hi everyone, welcome to our webinar for today, and we are going to start. So I'd like to thank everyone for joining the webinar today, and I hope that you would appreciate the learnings that you would have. And I'd like to see if everyone for the last time can hear me or see me well. Can I have a thumbs up from the chat box from everyone? Okay, thank you so much for confirming. Just want to make sure that everyone is going to have a convenient time during this session. Thank you. So let's now go ahead and start. So let us make sure that we won't be distracted by some notifications and sounds. So I'd like you to go to the lower right corner of your screen. There is a gear icon there right beside the X button with the purple background. Okay, and click on that gear icon. Go to notification settings and make sure to uncheck all the boxes there so that you won't see any notification popping up, and so that it won't block your screen and won't distract you during the session. Kindly give me another thumbs up when you're done doing that, and just let us know if you need further guide on that one. All right, I can see people giving me the thumbs up for the notifications part. So if you have questions about how to do it, you can just post it in the chat. I'll go ahead and give you the instructions again later on. All right, so for today's session, our topic would be about composite materials in construction. And this is going to be presented by Dr. Igor Shufrin, and he is one of our lecturers and unit coordinators at EIT. And later on, he will be introducing himself as well. So about the copy of the slides that we are going to present today and the video recording of the webinar, we will be giving a copy and of the video recording to everyone, and that is after the webinar session. Most likely we will be having that available in the next 2 to 4 working days, and the certificate of attendance as well. Please note that you should use the QR code or the link that I will be posting later on to register and request for your certificate of attendance. And again, it will be available or will be sent to your email in 2 to 4 business days as well. So just a little bit of background about EIT. So we are an engineering school, and we are based in Perth, Western Australia, and we are also one of the very few engineering specialists institute in the whole world, and we deliver a lot of courses ranging from professional certificates to diplomas, advanced diplomas, undergraduate and graduate certificates, higher education courses like bachelor's and master's degree courses, and even a doctor of engineering course. And the good thing about EIT, or what makes EIT unique, is that we are industry oriented. Our programs are designed by industry experts, just like our presenter today, Dr. Igor. And we are ensuring that our graduates would have cutting edge skills, and these skills will be valued in the workforce. And of course, we also make sure that our school and our facilities would be up to date with the rapid technologies in the industry. And we also have world-class Australia accreditation. So we have international accreditation, and we also have accreditation from Engineers Australia in some of our courses. And that would be in the Sydney Accord, the Dublin Accord, and the Washington Accord as well. And for our other courses, they are all accredited by the Australian government. And of course, we are proud to have industry experienced lecturers, just like what we are having today, because we would like to ensure that our students would be exposed to the up-to-date or the latest trends in engineering or in the industry. And of course, these lecturers would be able to give practical, updated insights about our engineering courses. And we also have a unique delivery model. We have a unique methodology, and that is through our interactive webinars. We also have live lectures for our on-campus programs, and we also assign a dedicated learning support officer for each course so that our student would be supported all throughout the course. And we also have state-of-the-art technologies such as our hands-on workshops, and also our virtual laboratories and our remote laboratories. So those are our simulation softwares. So our practical activities for our students are really close to reality. And that's it about EIT. Now I'd like to introduce Dr. Igor Shufrin. Again, he is one of our lecturers and unit coordinator at EIT, and I give him the liberty to tell more about himself now. Thank you so much, Dr. Igor.
Hi, Lisa. Thanks, Lisa. Can you hear me?
Yes, we can hear you well.
Right. Thanks, Lisa, for introduction. So I think the stage is mine now.
Yes, that is correct. So you can tell our participants something about yourself, or yeah, and you can go on with your presentation.
All right. Oh, thank you very much, Lisa. Yeah, about myself, I'm a big fan of hybrid structures and materials. There's a researcher and a lecturer for the last 20 years, so I've got quite an experience. My research topics involves the composite materials, computational modeling, composite structures, mainly for civil engineering, but not only. There are some projects involving the drilling projects, so we can model technically anything which is moving, vibrating, and can be made of composite materials. Right. So, and today I will be talking about application of composite materials in construction. So I will probably share the screen first. And it should be this. Right. Looks right. All right. So, the topic of this webinar, of this presentation is composite materials in construction. Like I said, this is a very exciting and innovative area, but the title sounds too broad to capture this in 1 hour talk. So we will need to narrow this down. So what I will do is I will focus on structural applications only. In the last 2 decades, the field of composites has grown enormously. A huge range of non-structural components is produced nowadays using composite materials, which include some architectural elements, building envelopes, thermal insulation, windows, smart walls, so many that, and they all belong to the area of non-structural elements. So they will not be our goal today. The main objective of this talk, of this webinar, is the structural composites, and they use in structural engineering. So I will first introduce the structural composites. Then we'll discuss some properties and how it works. Then we will see how they can be used in structures, in structural engineering. We will discuss concrete reinforcing. We will discuss strengthening of existing structures using composites. We will, at the end, touch base with some hybrid structures which incorporate composites as well. And I will summarize this by defining a set of variables for design of composite structures, and we'll have some time for questions and answers, Q&A session. So let's start from some definitions. A composite material is a material made from 2 or more materials that are combined to produce a material with a third material, actually new material, with enhanced or unique properties which cannot be achieved by the original components only. Well, this is a very classical definition. There are many types of materials that fit this definition. I believe the most famous one is the reinforced concrete. You would feel that I definitely have very strong structural background in civil engineering, because we're dealing with concrete today, but I also believe that the first ever composite material is the RC, reinforced concrete. Well, that combines, it fits the definition, that combines steel and concrete in a way that they complement each other. Well, the resulting material, no concrete, neither steel. But where's the limit? In the structural engineering, we have some ratios, so-called reinforcement ratio, which we use to define the amount of steel in the concrete. So in the world of composite materials, we use a volume content of fibers. We will get to this shortly. So when we combine 2 materials, we call one of them is a matrix, and another one is a filler. So the matrix should be continuous. Often it's usually we will get to this as well. So it's some kind of a resin, epoxy resin. The matrix binds together the filler face, which should have higher strength and stiffness. So the filler must be stronger. So altogether they will form a new consolidated structure. So to create a composite material, we need to satisfy 2 conditions. The connection at the macro level. We're not talking here about molecular or atomic levels. We're not designing any new chemical compositions. We're talking about combining materials in the macro level, which, simply speaking, we can touch. And the second condition is uniformity of resulting material. As a result, if we satisfy these both conditions, the mechanical properties of the resulting composite can be defined as effective property, as some homogeneous effective property. And no matter if I take a flexible matrix and hard filler, or I'll take a brittle matrix, read concrete, and tactile filler, or I will take a hard skeleton and embed it into the matrix that protects it in terms of temperature or corrosion. So if this action is uniform, the material, the resulting material, is a composite. So with these composite materials, we're opening the range of possibilities, infinite range of possibilities. We can achieve different goals. We can increase strength and stiffness. We can reduce weight, which usually comes as the specific strength and stiffness, because we want to achieve some strength as per unit weight, right? So we can improve wear resistance, durability. We can play with thermal properties. We can change it from positive to negative, the thermal expansion, for example. So the list is long. The performance on composite depends on the properties of the base material, of course. Geometry of the fibers. This part is completely clear to structural engineers, right? Well, we know if we change we know where to place reinforcement rebars into the concrete plate. The quality of the interface between the materials, so we need this complete bond between them in order to ensure the uniformity. All right, so as a result, often we should not mix the uniformity in isotropy, because the composite materials are anisotropic in nature, so they have different properties in different directions, even though they're still uniform. So in this anisotropic nature of a composite lies the main advantage. So we know that reinforcement can be designed to follow the stress pattern in structural analysis. In concrete design, we know this. That's what we do. We use the reinforcement in the places where we need it. So similar idea can be used for composite materials. So we can improve the performance, and we can achieve the much better performance than the traditional isotropic materials. So there's some classification. So this classification of composites follows the basic concept we defined earlier. A matrix made of one material being reinforced by another material. So the reinforcement then. A second. So the reinforcement phase can be either fiber or particle. So both can be random or randomly oriented or arranged in a certain way. The fibers, which are more important for this talk, can be short or long. Can be short, oriented randomly or arranged in a certain way, and they can be long. So the long fibers are usually continuous and can be set in one direction, two orthogonal direction, or in any predefined angles. All right, so we have all these options here. So, well, next, we will have some brief insight in the properties of matrix and fiber materials used for structural composites, and then we will look at the effective properties we can achieve using them. So first is matrix. Oh, the role of the matrix space, as I mentioned already, to bind the fibers together and to protect the surfaces from external influences, abrasion, environmental degradation, and so on. The matrix also should maintain the position of fibers because we arrange them in a certain way. The matrix also transfers the stresses to the fibers by adhesion or by friction. This requirement should be coupled with adequate matrix shear strength. In addition, the matrix has to maintain the chemical and the thermal composition, so compatibility with fiber, so they will not affect each other chemically. And the matrix provide the color and surface finish for the aesthetic view, so for any architectural elements. So the matrix materials used in structural composites are usually polyester, featured by the polyester actually featured by low cost and easy application. However, it's quite sensitive to UV lights and has quite moderate mechanical properties, what we see here, and not so it's only about 40 to 50 megapascal strength, and modulus of elasticity is up to 4 gigapascals, so not great. The next one is coming vinyl ester, which is a higher chemical environmental resistance. Mechanical properties better, and that's better than the polyester. We can see here was increased ultimate strength already to 90, which is actually the vinyl ester, due to its relatively low cost, is the preferred material in construction industry, which is slowly changing nowadays. So the disadvantages of this is sensitive to heat and still higher cost, but relatively cheaper in comparison to the other ones. So the polyurethane is the next one. This is probably the best. Doesn't really appear in my table here. However, because it's still too costly for construction, that's the only reason. So the higher strength and flexibility, very high chemical and environmental resistance. So it is very, very good material for this. The main disadvantage of this is the premium cost. It's about 1.5 times costlier. Costs more than in vinyl ester. Well, there's some most useful, most popular one also, which you hear everywhere. It's epoxy resin, which provides high strength and flexibility. It is high moisture and temperature resistance. So this and moisture and temperature resistance. All the curing time is a bit longer, so we can provide longer working times, which sometimes becomes important. The cost is still a bit high, but it's getting better nowadays. And the critical mixing consistency is a bit hard to get, but again, that's our problem in construction industry. We need to improve the quality controls there. So the epoxy is commonly used in aerospace applications, while the vinyl ester is quite popular in construction industry nowadays, but it's actually turning towards the epoxy. For premium application, there we've got this polyurethane. What I also highlight here in this slide is it's the coefficient of thermal expansion is relatively high for all of these matrices. So in comparison to steel and these units, you can see that steel is the CTE of about 11, 12, while the vinyl ester is about 18. So it's 8 times higher. Well, next, fibers. Fibers, all different fibers, but not those fibers we use in structural composites. What we use are this kind of fibers. So the fibers that are mainly used there are carbon fibers, glass, aramid fibers, some boron recently. So the fibers can be short or even chopped, you see, long unidirectional or interwoven. So they are often saturated or coated with the material, so which is called pre-preg, pre-impregnation, with the resinous material, the material which provides some interface between fibers and matrix. So most commonly, that's the same material as the matrix. So they come in forms of rovings, bundles of continuous filaments, mats with short or continuous filaments, randomly or specifically oriented, woven or non-woven, all different options. The carbon fiber is the most popular one. It's the higher modulus, high strength. So we've got this in this table. So carbon fiber, elastic modulus, tensile strength, the ultimate strain. It is quite strong. What you see is the tensile strength of carbon fiber reaching 5 gigapascal, which is in comparison to hundreds of steel. Right? The elastic modulus is also much higher than the steel. I will remind you that the steel has 200 gigapascal elastic modulus, or here we're reaching for the some grades for 450. The carbon fibers are used for cases when we need material with higher modulus and higher strength. And another interesting one, it's not here in the table, but I highlighted here, and the carbon fiber actually has the negative CT, negative thermal expansion. Wow. So carbon fiber can be produced from different sources. Pitch fiber is probably the cheapest ones, derived from the petroleum asphalt, coal, and PVC. But if you see that in terms of the pitch fibers, in terms of elastic modulus, they are quite strong. However, we're losing in terms of tensile strength. Right? Glass fibers. Glass fibers are more popular in construction for structural applications. They're cheaper. So this is the silica-based glass compounds with relatively high strength. So we see this can come to again quite 4 gigapascal, 3 gigapascal. We've got 2 grades. One is called E-glass, general purpose structural applications. There's E-glass, that's the one E. Another one S-glass, for which it's got higher strength and heat resistance as well, and the higher spec of X2. It's glass fibers. There's another kind of is aramid fibers. It's produced by extruding and spinning the solid fiber from a liquid chemical blend, so aramid. They retain they quite good in retaining the mechanical properties, aramid fibers, so up to 400 C degree, they retain the mechanical properties up to this temperature. They don't really, all of these fibers don't really rust or corrode, and not really affected by moisture, the fibers itself. Why? Especially aramid fibers. So from here we can get to structural composites, to the performance and properties of the combined material. So the obtained effective properties. So when we mix these fibers into the matrix, the obtained effective properties depends on a couple of things. So first of all, it's fiber architecture, which includes the type of fiber. When we use carbon, glass, specific strength, and fiber volume fraction. So it is probably most important variable here, fiber volume fraction. So typically we call composites with up to 30% of fiber volume is the low strength, the low volume. So high grade composites, on the other hand, sitting on the other end of this range. So they actually have up to 75% of fibers on volume, meaning they only 30% left for the matrix. The high volume composites obviously made off-site and some controlled manufacturing conditions, while the low ones can be prepared and made on-site, which is often used. So another parameter is the fiber orientation, which affects the properties of the composite. The number of layers as well. So actually, when we talk about laminated composites, so we actually arrange these, especially woven ones or unidirectional long fibers, in layers, and then we've got some special spatial orientation as well. So type of matrix is the next parameter affecting the structural properties of composite. And what's an important part for the matrix, the void ratio. So often it cannot be porous material, so it's 1%. So the void ratio must be less than 1%, which is quite strict requirement. The quality control during manufacturing is vital, essential. So to achieve good fatigue properties, the control of the manufacturing is important. What is important there, the rate of curing. So it is affecting the properties of composites. It's one of the important parameters. Oops, sorry, too quick. So the structural, let's have a look what we get. The structural composites, what we normally call, so when we already seen matrix and the fibers, so we've got so-called CFRP and GFRP. And the C stands for carbon fiber reinforced plastic, and the G stands for glass fiber reinforced plastics, or polymers. And for this case, probably the better abbreviation would be polymer. So we have this. That's the FRP stands here. So we've got carbon, and we've got the 4 examples here: glass and carbon reinforced FRPs. And when we look at the properties, we can clearly see that the fiber volume is most critical one. When we increase the fiber volume, we see the best Surely the best properties in this column. Right. What else can we see from here when we look, for example, in the tensile strength? Longitudinal in direction of the fibers, transverse perpendicular, transverse direction to the fibers. So we see that the obtained material is highly orthotropic. It is very strong along the fibers and very weak in the transverse direction. What we also see that the shear performance is also on the weak side. So in plane shear, there's some numbers. A lot of plane shear not even exist for carbon for CFRP, carbon reinforced polymers. The failure and then when we're talking about strength, so actually strength and failure modes depends on the interaction between fiber and matrix. The main problem is that the fiber and the matrix have different values of strain at fracture. When one with the smaller fracture strain fails, the load is to be transferred onto another one. All right. And the tensile strength, we look at the tensile strength and compressive strength. So tensile is mostly defined by the fiber strength. So the matrix does not contribute much, while we look at the compressive strength on top of the failure of the fibers, of the strands, we have the buckling of fibers as well, which can be in phase buckling of fibers or out of phase. The in phase will be a little bit stronger, and when we have to remember that this fibers they sits inside the matrix, so they're not freely move, but the matrix is fairly flexible, so they will allow buckling as well. So when we look at this strength of this graph, I brought this graph on to discuss the failure modes a little bit. So what we're looking at the stress generation in composite with a matrix having a greater strain in fracture than fiber. So that starts here. For a low fiber, so we have the fiber volume on the x-axis, and we have this curve defining the strength of the composite. So for a low fiber volume, the strength is provided by the matrix over here. Okay. All right. So well, this, if we look at this dashed line, theoretically, if we have only matrix, so starting from this point with 100% matrix, it will go to 0, then the matrix volume fraction of the matrix is 100%. No, that's 100%. Sorry, the 100% is the fiber volume at this point. So the matrix volume fraction is 0, right? So which is opposite in this point. From this point, the strength is provided in this point. The strength is provided by the matrix. So when we increase the volume, fiber volume, the strength is increasing, and the larger stress is transferred to the matrix every time the fiber fails. So, if the matrix can carry it, we will see in this zone multiple fractures. Right. Now, if the fibers are brittle, which often it is, where will this curve will be sharp change at this point of the intersection. Well, there's some ductility in the fibers always exists, so this curve is quite smooth. Now we can summarize all of this into some design spec. So design spec, or simply speaking, everything we should consider designing composite structure. So a couple of points here. Low shear strength relative to tensile. I mentioned this. Low stiffness, relatively low. We can see this, the effective modulus of elasticity, low stiffness in the composites in comparison to steel. We're talking about very strong, very high strength, but the stiffness is not that high. So G for P has low than steel length modulus, C for P higher, but not significant. We didn't because, well, we only have 1 hour, so I skip some parts. The composites are very susceptible to creep. Creep is a big issue, and we will see, we will note it a couple of times today. So what is creep? So well, there's some continuing deformation under sustained load, which means that keep the dead load stresses under 20-30% of FRP ultimate strength. So we can have to reduce the calculated resistance by about between 20 to 30% due to creep. We have mentioned low UV resistance, which has to be considered. We have mentioned anisotropic properties, which can be beneficial. And in the thermal properties, in this spec are important, and they're different from normally used in construction and structural engineering because the C for P coefficient of thermal expansion can become negative with the higher volume content of fibers. Because we said the carbon fiber is negative CTE. So if we mixed quite sufficient amount of carbon fiber into even the positive CTE matrix, the effective CTE will become negative. A couple of more design aspects. The connection in composite structures. Connection is becoming an issue. And when we introduce the composites into the construction, it's common to construction site methods of welding and bolted connections becoming useless. They cannot be used with composites. So what we use instead is a high performance adhesives and mechanical connection. Well, a bolted connection is also mechanical, but it's not really adequate for composites due to the high flexibility of the matrix. Plus, we don't really like holes in composites because if they go through the fibers, so they will actually increase, they reduce the strength and this and weaken the material in this particular points. All right. The fire and heat resistance, that's another important consideration here. The fibers and matrix behave differently in a fire. The fibers are relatively non-flammable. However, in high temperature, they become softened, char or melt, and the mechanical strength can be reduced. On the other hand, most of the resins used for matrix have low carbonization and continue to burn in fire. They will also soften until they reach the polymeric glass transition temperature, which will change the properties considerably. So it needs to be preventive. So some preventative steps must be taken. So we need to prevent a flame spread by using we can use higher volume, higher fiber volumes, and restrict oxygen access to the structure, and we can use some flame retardants. So we're getting at this point into the composites in construction, so where it can be used. So composite materials are used in structures for, I classify this into 4 general groups. So the first, the composites can be used as a material for the production of reinforcement elements, and they are already used there. So it is the rebars for reinforced concrete. So then we will call this reinforced concrete, we'll call it fiber reinforced concrete, FRP reinforced concrete to be precise. Another possibility here is the cables for pre-stressed concrete for both pre and post tensioning. So that's some rebars here, some tendons, and the other forms, shapes of pre-stressing elements. That's one application. Another application is the strengthening of existing structures. So fabrics for external reinforcement of concrete, wood, and even steel structure. Some kind of applies here, right? Some reinforcement plates and strips which are bonded to the stretch side. You will see the stretch side of beam or a ceiling. Right. Filament winding of concrete and wood cores for some posts, like you see here, this example. For electric poles, it is also used for railway sleepers to wrap them and provide additional strength and stiffness. That's the second. The third application which is gaining popularity as well, the production of profiles of composite materials. So the entire profile of beam can be made of composite material, which makes it 10 times lighter. Well, I remember many years ago when some project on drilling engineering, when they were introducing drilling pipes made of composite materials, when one of the participants was brought them through the meeting, was carrying on his shoulder about 3 or 4 pipes of a 10-inch diameter and 3 meters long, and he brought a bunch. To lift one of them made of steel, you would need a crane, and it was quite impressive. So this application is becoming very popular. So production of profiles of composite materials, so some beam, girders, and panels to support large loads. It comes to bridges. There are a couple of examples. This particular one here of the fully composite bridge made of composite materials. It is also a good option for trusses because they the elements will be slender, which is our idea of a truss. They can be also used for columns, posts, and piles to carry vertical loads in corrosive environments, marine structures of different ferries, jetties, and so on. So the last case, so that's the last one, is the composites were used for the hybrid structure. So then we're expanding this definition even further. So what's the hybrid structure? So the hybrid structure is a structure which using many different materials, right? Not only is the composite as a material, but combined already on the structural level. Like for example, this beam here, what you see, I'm not going to get in much details for this, but this shell, which forms stay in place permanent formwork, I'm talking about 20 meters span, made of composite material. Then this formwork is brought on site. It's some American company. If you have heard of, not, it doesn't. They actually selling these beams. So they brought the very light formwork and strong at the same time. They have some special arrangement for reinforcement. You can see it here. Some another structural idea of arc here inside this line, and then they actually cast concrete in place. But the assembly is way too easy because every assembling 25 meters span is so easy that you don't need heavy machinery. And pumping concrete doesn't require it at the end. That's one example. Hybrid structure. So like we mentioned, this warp here with some corrosion-resistant composites for the columns, and very simple sandwich panel with composite faces and some cellular core. So combination again. So we're expanding this definition of composite material into the hybrid structures. So they're getting to the next level of creativity, I believe so. All right, next. So let's have a look. We have a bit closer look. I don't think we have that much time, but I will have closer look at FRP reinforced concrete. We will touch base with the strengthening, much shorter, and then we'll look at some quick closer look at the examples of one of the examples, at least at this bridge, more pictures. Right. FRP reinforced concrete. The structural idea of FRP RC, FRP reinforced concrete, does not change. Well, the idea is to provide the concrete with tensile strength. That's what steel does in steel reinforced concrete. So all the shapes of the rebars and the shapes of the rebars and the stirrups also the same. It's similar to steel reinforced concrete. The materials used are CFRP and GFRP, the diameters ranging from 6 to 36 millimeters, and that's already in the production line. The fiber volumes higher, they should be higher than 50% into these rebars, right? Into these rebars, all this kind of rebars. What is different? Everything the same, but different. What is different? Well, these rebars made of FRP cannot be bent on site like we can do with steel. So they must be the whole arrangement prepared off-site to the final specification. So all these shapes must be done properly to the proper sizing off-site and brought to site for casting, for pouring concrete. The other difference is the end fittings, especially for cables, be different end fittings. and the adhesion strength is low between the concrete and FRP, is lower than the steel. But that's a minor problem because we're using all different rib profiles, right? All these rib profiles. Also, there are some methods which are improving this connection, so increasing this adhesion or improving the pull-out resistance. So if we compare this to steel, the methods are different coating. So we see various surface finishing, so it's different coating, ranging from coarse sand or somewhere that's the sand, fine sand, glass, so to improve the adhesion. Like in the steel bars as well, so it's a little bit harder to make here than these ribs, so it can be done by some helical rock, for example here. Yeah. But in general, all this brings that the pull-out resistance of FRP bar is higher than steel bars. Can be right. Design. So we're looking at the ultimate limit state. I believe many of you are familiar with the idea of limit state design. So we've got ultimate limit state, sometimes called strength limit state, but it includes more than strength, includes stability, includes the includes the fatigue as well, and serviceability limit state. So we will address here too. So ULS and SLS. So in ultimate limit state, design of the concrete FRP, reinforced concrete, or GFRP rods, CFRP rods, is similar to conventional concrete. That's what we say. So we only highlight, I'm looking at the difference. I will try to highlight the differences in this design. So the strength of the GFRP bars or FRP bars decreases when the rod diameter is small. Right. I've got this picture here. The strength when we're using small diameters rods, they only have this range of strength. When we're using, let's see, on the other end of this range, it is decreased by about 50%, from almost 900 to 480. Right. The modulus, though, doesn't change much. You can see well, it stays at the same range. So this can be explained by the fact that the stress developed at the fiber located near the outer surface of the rebar is not fully transferred to the fibers located in the center. So actually, part of the fibers are failing while we still in the most of the section is intact. Right. What else? FRP rebars are usually elastic and brittle. So the stress strain curve is linear until failure. The FRP rods should only be used at service temperatures below glass transition temperature. So we have this limitation of the temperature. As with steel bars, FRP reinforced concrete design is carried out using only a longitudinal properties of the bars. That's the same, actually. So since the FRP bars are linear elastic until failure, the formation of plastic joints and redistribution of moments is statically indeterminate, which makes it harder to design. And due to the creep and fatigue problems, FRP bars, especially GFRP, may fail catastrophically under continuous load at stress levels which are much higher than the ultimate tensile strength. The brittle failure of FRP, the outermost layer of the bar must be used in bending tolerance calculation. So it's a bit trickier. So let's have a look at the serviceability limit strength, which is actually in this case will be a more important. So, well, FRP bars typically have a lower modulus than the of steel bars. So, at serviceability limit state, deflection and crack weights can often control the design. The crack. So, if we look at its American code, so permissible crack widths for FRP and steel RC structures, if we compare this with steel, we can see that the permitted crack widths is in concrete structures in FRP reinforced concrete is greater than in steel reinforced concrete. The reason is simple. We don't have corrosion problem, so we don't need to defend steel from influence of environmental influences. So the other thing here is the limits on the service loads are much higher in this case. So the limit factors we're using for serviceability limit staying are higher, and that's again due to the creep rupture, due to the creep problems. So they can go for the limit fibers up to 45 strength reduction. So the design resistance, the resistance factor will be much lower. Right, the main difference between design of FRP and steel reinforced concrete is due to the fact that the failure of FRP is brittle. So, and failure of steel is ductile. So as a result, the steel reinforced concrete is under-reinforced, which means the rebars yield in tension and then concrete crushing compression. That's what we do in conventional concrete design. What happens with the FRP is essentially over-reinforced because the concrete will crush under compression first. It is before there is strong fibers, very strong rebars will yield. They do not yield, but they fail. Well, it is actually possible because concrete does have some post-peak strain capacity. Let's have a look at this. They got an example of some typical FRP reinforcement cage, and which needs to be pre-manufactured off-site. The failure of FRP reinforced concrete here, that's the example. That's what I just mentioned. We can see beams are failed due to crushing in concrete in the compression zone, or debonding of stirrups over the tension zone. So it's not really, can't really see here on this small picture, but it's there. Also, we can notice the large diagonal shear crack here due to the low shear resistance or shear failure as well. That's the main failure mechanism in FRP reinforced concrete elements. Right, so when we look at the computation of flexural strength of fiber reinforced FRP reinforced concrete, excuse me, we use this common reinforced concrete model. Right, reinforcement, concrete part. Anyone who does structural engineering very familiar with this, and even in solid mechanics is discussed. So some kind of a hybrid structure. Due to as the FRP reverse has very high stiffness, the neutral axis here, this neutral axis, can be very high. That means this compressed concrete zone will be small. When we calculate the C, well, I just shortened a couple of slides. I believe if you download the slides you will be provided, there will be a couple of extra slides there with more details there. We don't have much time to go through them. So when you calculate this C, it will become, and I will find out that it's quite low, because the stiffness of the fiber here is high. Other problem is there is a well known for structural engineers flexural resistance factor 0.9, which is used for ductile failure of steel reinforced concrete. And in this case, it cannot be used at all, so the resistance factor is low to 0.65. Now, all standards technically allow the use over or under reinforced design for this. However, the serviceability limit state, the deflection and crack weights will impose higher reinforcement ratio. I didn't bring the expression here again, giving the general picture. So the higher reinforcement ratio means over reinforced conditions. So as usual, in this case, the nominal moment capacity, this one is defined as a couple. So these two forces, we take this lever, calculate this couple, we have this tensile, the force into the reinforcement, force in compression. So that's how we calculate the nominal moment capacity here. However, when we use this case, we cannot use the yield in steel reinforced concrete. We use yield strength of steel to calculate this force. We cannot use it here because there is no yield. Right. The shear resistance. Let's have a quick note into the shear resistance. So the shear resistance of steel reinforced beam is provided by shear strength at the top part when it's not cracked, by so-called aggregate interlock, which is the friction between two sides of the cracked beam or two sides of the crack. And then dowel action of the main reinforcement, tensile reinforcement bars, or dowel action, arcing or elbowing action between the parallel tracks. Right? When they want to rotate, they actually elbow each other and they cannot move, so which provides additional shear strength, and the shear reinforcement which we add there. However, what's the differences when we look at the FRP RC beam? The shear strength of the top part is not the first one. In practice, the differences again. The depth, like we said, of the neutral axis, the compressive part of the concrete is quite low, so much less. So the contribution of this will be insignificant. Aggregate interlock. What happens with aggregate interlock? The weights of the critical diagonal crack in FRP reinforced beam is likely to be wider because the flexural stiffness of FRP, actually over rebars, is lower. The strength is higher, but the stiffness is low. So it's likely to be wider, which means we'll be reducing this contribution as well. Dowel action, the third one. Well, the problem is that the shear resistance of FRP bars is lower. We're also losing on this. What about the elbowing? Elbowing actually stays about the same. But this becomes only significant if we have deep beams. Otherwise, this effect overall for very shallow beams is already insignificant. The shear reinforcement, well, this calculation I say put here not trivial. The stirrups do not yield, so the stress and FRP stirrup cannot be calculated in a simpler manner. No? Which is not force in the steel stirrup, which we actually use as a displacement in the bar. So this calculation is not trivial. However, we still need some codes for this. Well, there are some already provisions. But overall, the conclusion for all this is that the shear strength of fiber reinforced beam, concrete beam, will be lower. So it needs some additional attention. We're still in time. Wow. All right. Okay, so the next part, well, probably we'll do briefly. Strengthening of RC structures is using obviously FRP or other composite materials. It is also very important and very popular application actually. Even it's become popular many years ago, and that's actually where the composites entered construction site for the first time, in the strengthening of existing structures, and the replacement. What's the catch? The replacement of the functionally deficient civil infrastructure is not a feasible option. In most cases, there are several reasons. So in most cases, they range. It is not optional in most cases because the reasons are range from economics, simple costs, to logistics and some social economic impact. So it's to remove the inhabitants there for considerably long period of time. Would it be just tenants or industry or some companies? So it's it can be quite cumbersome. So a large percentage of concrete structures that were built in 50s and 60s, although still in good condition, they do not meet the current requirements, current standard requirements, especially bridges or current traffic loads. The seismic standards are have changed. So, and another thing which can affect this is the change of the building purpose, so different usage for a building or structure. So all this leads that we need the structures needs to be improved, needs to be straightened. Some of the structure has deficiencies in the design materials, and so on. So deterioration of materials also a problem. And if we want to retrofit these structures using conventional techniques, well, it is obviously possible, but involving some problems of removing people around. But in many cases, it cannot be done due to some structural reasons or functioning reasons. So we cannot add more steel. Simply speaking, we cannot add another steel beam into the car park, right? Because then we will lower the clearance and it cannot be used for some. So we will reduce the clearance in the car park, so we're reducing the use of it. So all different reasons for this, and the use of the fiber, FRP composites, presented itself, and like I said, 20 years ago, as an attractive option in all these cases, and it has become very popular since then. And let's have a quick look at this. This strengthening system include mainly we can distinguish two. So one is laid in place FRP sheets. So the laid in place meaning that's the actually such the fibers coming on site in the form of fibers or some mats, woven fabrics, and they're saturated with polymers on site. That's what you see in this picture, actually, this one. As on site, and they cured in the field, and they simultaneously at the same time create a bond between FRP and concrete. So when you actually do like this lay in place cases, that's the resulting bond. Well, actually apply the sheets of the FRP sheets, only the woven fabrics, and then they apply the polymer here, applying the polymer, producing some kind of FRP on place, on site. Well, it is definitely will be lower volume of fibers, because we cannot do this manually. The other way is use some procured systems, so ready off-site manufactured composites, and they will be bonded to the structure on site. So in this case, mostly unidirectional laminate strips. So what's in this picture? So no, this picture, this one. And strips and plates with high fiber volume content. And the other option is actually so-called near surface mounted strips. So for this case, the cuts the slots are so cut here. See, that's here, slots. Relatively low depth, about 20 up to 25 millimeters, and then into these slots, FRP strips are easily bonded, so providing the additional strength here. That's the procedures, that's the systems. In terms of the structural terms, the types of strengthening should be selected by the type of resistance to be improved. So if you want to improve flexural resistance, shear, or axial strength, axial resistance, or we will call it flexural, shear, or axial strengthening. So the flexural strengthening is used for beams, slabs, and walls. It applied at the tension side of the beam, the tension side, and go aside, but there's no point to apply it higher than the neutral. And there's no point to apply that in the compression zone, because it's not going to work there. So the fibers actually, the fibers will be oriented along the axis of the beam for this case. The other one is shear strengthening, which is used for beams, columns, and walls, and it applied on the side. Well, it can be even go all the way around, wrapping the whole wrap. The fibers in this case are oriented perpendicular to the axis. The axial enhancement is done by providing a confinement around the compressed member. If this is my compressed member column, axially compressed, so we provide a confinement and which will restrict the expansion under axial compression and will improve the resistance. So the fibers in this case are oriented in circumferential direction, so around, actually winding filaments around the column. Right. So flexural strengthening, let's just highlight a couple of things. Flexural strengthening by FRP is similar to strengthening by adding steel plates. So we would add them in the tension side of the element. But there are obviously some differences here. And besides the difference that the steel, we need to add massive amount of material, and the FRP will add very thin plies, and it will be easier and it will not require stop functioning the building. But structural differences, that's what I want to highlight here. What's the difference? The number one, we've mentioned it many times today already, FRP does not yield. Brittle. FRP is more susceptible to delamination failure. It can be, the stress level in FRP can be much higher, which needs to take into account. The analysis and design based on assumption of continuous transition and equilibrium of tensile and compressive forces, which is similar to the design of steel reinforced concrete. That actually means a couple of things. No slip between FRP sheets and concrete. The adhesive layer does not deform and shear, and this assumption is actually will hold to even after the reinforcement steel yields. So in this case, I have to highlight this. We have three materials here. We have FRP, we have concrete, and steel. Right, and altogether, this strengthening is only possible when there is a sufficient additional compressive capacity in concrete. Because the concrete must allow the increase in the moment capacity. Otherwise, we wouldn't do anything in this. And this is possible with relatively low reinforcement ratio. The failure modes, I will probably skip we'll see. So the failure modes. The failure modes, we're looking at the flexural FRP strengthening, which is the most popular. The failure modes, there's attached layer of FRP on the concrete, steel reinforced concrete beam, loaded and bending. So the modes are concrete crushing before steel yields. There's nothing to do with the FRP sheets. Steel yielding, but FRP sheets changing the equilibrium in the cross section. So the steel yields followed by concrete crushing. That's what we actually one of the preferred modes. Steel yields followed by FRP reaction. It was actually preferred mode. The shear failure of concrete initiated at the bonding surface, so it initiates here and propagates towards the top. It's another failure mode. Well, these modes become important when we design it, so we need to consider when we calculate the resistance. So another three of them, and there's the delamination, the bonding comes in. So the shear tension delamination, so it starts at the top and propagates towards the middle. The debonding failure, so it's actually, again, it starts in the middle and then propagates at this point. The bonding failure is when the intermediate crack induced interfacial debonding. So we have the crack here starting at these points, which actually initiate the crack, and it will propagate in the crack between the new strengthening layer of FRP and existing concrete. Right. Well, these debonding failures are a problem. They're very much known to the engineers. That's why many of them were reluctant to use it for many years. And we're still getting convinced, and they're slowly getting convinced. So no reliable analytical method to predict the bonding failure is available. There are some models around, and experimental observation and so on. So what instead the American Concrete Institution Guide, American standard, proposes two ways. So the bonding can be prevented through some special end anchorages. So we will use special anchors to prevent the debonding, or simply speaking, some kind of high strength bolts there. I've seen these designs, just going through to prevent this debonding. And the other way is in design, so to limit the strain in the FRP layers. And the standard actually provides some expression to calculate it. So the moment capacity, the nominal moment capacity of FRP strengthened cross-section is, you can note the similar picture. Now we have the compression in concrete and two tensile parts. So the procedure is iterative. First, we estimate the neutral axis depth at this position. Then we need to determine the modes of failure, which are two. The preferred one I mentioned. Compressive failure of the concrete. That's the mode one. And mode two, the failure of FRP strengthening system. So FRP layer breaks. Then we will calculate strains and stresses and recalculate neutral axis until the procedure is converged. And then we can calculate the moment capacity once we found the axis. I will avoid showing you any expressions for this. It's probably more interesting for practical engineers who wants to do this, but then they open the standard. But that's the idea. Is the concept is definitely here. Right, the shear strengthening. Well, then they need to compose the concrete, steel, and strengthening sheets. Let's go even faster from here. They all have different design factors. And like we said, it can be done two-sided, three-sided, or four-sided. In four-sided case, please note there is no problem of the bonding because it's fully wrapped. And right, so in this case, the splice will provide some additional shear resistance. Wow. We probably running definitely out of time, but we will so skip probably these hybrid structures, which are fully first composite bridge in Denmark, built in '97, fully of composites. So all elements are FRP, easy installation. I will skip details on this. There are many more built since then. Right, the FRP bridge decks getting more popular, though it's very corrosion resistance. All different elements readily produced in different countries today. The design aspects, they need to be considered the connection, we mentioned it before, and there are a couple of more. The connections are mostly done, as discussed, using mechanical devices and adhesives. And another more example of hybrid structure, so presenting a combination of steel girder, FRP deck. If anyone who is familiar with steel concrete composite construction, which is steel and concrete, in this arrangement, they are actually, in this case, has a concept from composite construction of shear stud connection is used. Another hybrid, for this case, it is steel girder and FRP deck, but the hybridization of concrete flooring and FRP beams is also becoming popular. So using FRP beams in addition to FRP reinforcement. So if you check it online, you will find a couple of nice examples. We'll skip them here. Already did. Well, let's summarize all this. So, when designing a composite structure that uses composite materials, you have to consider the following parameters. So it will be type of fiber, the fiber volume, the orientation. We didn't actually look at the different ones, only 0 and 90 degrees, so in two directions, but the possibility of angle plies is very interesting, especially for some kind of pipes and round cross section. It becomes very interesting, improving, because then this orientation, fiber orientation, improves the shear resistance, which we said was the problem. So type of polymers, resin, and that's another consideration. The cost, which is related, the resins, the polymers becoming cheaper, so it is becoming more available, more feasible for construction. And all this obviously related to how it can be manufactured, so we can afford it or not. All these variables will lead to optimization of required physical properties, such as tensile strength, compressive strength, stiffness, weight. So environmental influence is also important here. So we will improve environmental resistance, fire resistance, UV resistance, and corrosion resistance. So not improve, we need to optimize this. We need to take this into account because these are the behavior of composites in this aspect is different from the conventional structural materials. Right. And to sum this up, everything, the message I was trying to convey here is that the fiber-reinforced composite materials are gaining strong popularity nowadays. Overall, everywhere. Now they're actually becoming a method of choice in structural engineering. It can be used for reinforcement for concrete structural members, and they're already used. But the more potential is into the pre-stressed and post-tension elements, or pre-stressed parts and post-tension tendons. And the other aspect is this, it's quite well developed part of this is the strengthening for existing structural members. It is quite well developed, and there are some codes for this already. So these methods for strengthening can be extended for the design of new structures. Another point I would like to highlight here, and it's about FRP profiles, the structural members made of FRP. Well, they still require, still require standards. We're still working on this. And the hybrid structures, which we didn't really touch base much, they present a room for creativity in the structural engineering. Right. So, well, it is all I have for today. There's some reference list, quite a lot of references, you can understand. And I didn't bring referencing for the standards here, so you will find them out themselves. Right, thank you. Any questions?
So, Dr. Igor, I think we have one question here in the chat. He is asking if is it better for fibers to be randomly orientated or oriented in the same direction as the bending axis to achieve strength, ductility, and resistance to crack formation?
Well, the optimum design can be achieved with some preferred orientation, right? Especially for the crack formation. But in practice, in some cases, and it is also popular, the particle reinforced concretes today or chopped. So it's just a general improvement of the effective property. That's there is a difference line should be drawn here. We can improve effective property by random oriented particles or short fibers. But if we use longer fibers, we can go and target specific loads, so we can be more specific. And when we're more specific, we can save more.
Okay, thank you so much for that. There is another one here. He is asking if what are the major component of composite used in building and bridge construction, and other than matrix and fiber.
So it's two questions or one? I missed here. It's the same. Okay. Can you repeat, please?
Sorry. Someone asked, what are the major components of composite used in building and bridge construction other than matrix and fiber?
Matrix and fiber, that's the constituents, components of a composite material. We're using fiber incorporated into matrix to receive the composite, right? And then this composite material should be used for creation of structural components. So in bridges, it is at the moment, it is mostly decking for structural beams, for pedestrian bridges, for other, for light bridges. It is the example, the example I showed, it was pedestrian bridge. For light bridges, so the beams are fully made of structural composites, FRP.
All right. Thank you so much,
Yeah, no,
Dr.
I'm
Igor.
afraid the question that's the way I understood this question. I'm afraid I cannot provide better answer than that.
Okay, thank you so much for that. So everyone, if you have further questions, you can just send us an email and I will forward them to Dr. Igor. You can send us an email to webinars@eit.edu.au. And I am now sending your link to request your certificate in the chat. And please note of our upcoming courses as well. We have upcoming undergraduate, bachelor, graduate, and master's degree and Doctor of Engineering degree programs that will be starting in June and in July. You can visit our website, www.eit.edu.au /schedule so that you can see all the list of upcoming courses that we have. And these are also our upcoming webinars. You can visit our events page on our website to look at our upcoming webinars. And in 2 to 4 days, we will be sending out the video recording of this particular webinar. And for those who'd like to use the QR code, kindly scan the QR code that you can see on your screen right now to request for your certificates. And for those who'd like to use the link, copy and paste the link or click on the link that I sent in our chat box right now. And again, for further questions, inquiries, and concerns, please send an email to webinars@eit.edu.au. I know that you have a lot of questions to ask, and we are very grateful for Dr. Igor that he covered everything in this webinar. And I do hope that everyone learned a lot, and a lot of you are saying thank you. You are very much welcome, and thank you also for participating. And here are our contact information. You can see our website link on the slide, and we also have our phone numbers and our email address that are direct to the webinar channels. So if you send an email to our webinars inbox, then we would be more than happy to assist you as well. All right. So thank you so much, everyone. Thank you so much, Dr. Igor. That was a very informative session, and I can see that every one of them also enjoyed it and find it interesting. So again, we will be sharing the materials in 2 to 4 working days. Thank you so much, everyone. Enjoy your day.
Thank you. Thank you. See ya.
See ya.